All right, I think we're going to get started here. Whoa, that was a really good marker. I think I'm going to steal that marker. Okay, last class we were talking about derivatives of exponential and logarithmic functions, yes?
Actually, is there, I ask a question or would it be better we can class?
Well, it depends on the question, sir.
It's about, like, one of the homework questions?
Yeah, you want to ask me a question about the homework? That's no problem. I can do that. What do you got?
So, it was, find the derivative of natural log of a minus x over a plus x.
Natural log of the square root? Oh, no. Okay. Natural log of a minus x over a plus x?
Correct.
Okay. So this is given to us. This is, they say g of x is equal to this, and you're asked to find g prime x. Okay, good. Good question. So first thing I'll point out is, or I'll ask you, is what is our independent variable? So what's the variable in the problem? Because we have both an a and an x in here. X, right? And then a then would be treated as a constant, all right? So when we look at this, we should be seeing we have natural log of a quotient, right? So we'll have to do the chain rule, because that's composition. So first we take derivative of the outer function, which is natural log. And the derivative of the natural log of anything is 1 over it. 1 over whatever is in the argument, right? So the derivative would be 1 over the argument. Right, I'll put it in parentheses even though we don't need it, but that's the derivative of natural log of something. It's 1 over it. And then times, now we go inside, look at the argument, and say to ourselves, what's the derivative of this? Well, this is a quotient, right? So we'll do the quotient rule on this. So I'll do derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. So the derivative of the top is what? So derivative of a is what? 0, because a is a constant, all right? Minus derivative of x, which is 1. So you just get negative 1 times the bottom minus, now what's the derivative of the bottom? A plus x, you're just going to get 1, right? Just 1. And then times the top. And then all over the bottom squared. That. All right, let's clean up the numerator. This is really negative a minus x. And then this really turns into minus a plus x, right, if I distribute the negative through. So what does the numerator turn out to be? Negative 2a, right? This is just negative 2a. All right, that's what the top is. And then also over here, 1 over a fraction is the same as the reciprocal. So I'm going to just flip this. This is going to become a plus x over a minus x. And then times, we said the top up there is negative 2a. And then over a plus x squared. Right? Like that. And we notice that this factor and this factor can cancel. You get that, and then one of those is gone. So I think our final result should be negative 2a on top, and then these two multiply together, right? Now I can leave them apart, or I can put them together. I'm going to put them together because I recognize that's a difference of squares factored. So if I were to expand that out, I get a squared minus x squared. That's it. That work?
Sure.
Okay, good. Uh-huh.
Couldn't you just do natural log of a minus x minus natural log of a plus?
Yeah, so I'm glad you brought that up. I was looking for my little towel over here. So that way right there required, you mind? Thank you. That way required a little bit of work because we had chain rule and then we had to do a quotient rule, right? And this was our final result. But if you start the problem out in the beginning and you do a little bit of algebra first, okay? So if we start out and we say, okay, we have a property of logs that says if we have log of something over something, that can turn into two logs with subtraction between them. So if I just rewrite this like this, using properties of logs, now I can differentiate that instead of the original one. And it's easier to do this one. Well, yeah, you don't have as much quotient rules. So the derivative of this, I do them individually because they're separated by subtraction. Derivative of natural log of anything is 1 over that anything, right? But be careful here, times the derivative of what's inside. So what's the derivative of this? -1. So I'm just going to make that negative on top. Okay? And then we have over here, let's see, minus the derivative of natural log of this is 1 over it, times the derivative of what's inside, right? Which is just 1. So that's it, right there. Common denominator. If we get a common denominator between these two, put them together, we get that. A little easier, I think, to take the derivative of that, but it's really up to you. Any questions on that? Yes?
If we did it that way, you would want it with a common denominator?
It wouldn't matter. On a test, I mean, like, this is correct. You know, we are getting very close to that point where we're going to start setting these things equal to 0. So at that point, common denominators are going to be something we're going to just have to do. Yeah, not today, but probably next week we'll get started on that. Oh, and I'll bring up, I plan on moving the exam 3, to what did we say, November 14th? I think that puts it a week early, maybe even more than that. It was originally on the 16th. Okay, it's more than a week. I plan on moving it to the 14th, and the reason for that is it'll reduce the amount of material on that test, and also it will allow anybody who wants to kind of see what their grade is after 3 exams, you'll know because it's the day before drop date. So I'll grade that test that night, and you'll post those grades that night, and that way Friday you can determine like if you want to stay in the class or drop the class. Okay? November 14th, yeah. I'll let y'all know more. It'll have less material, yes.
So the other material will be just
It'll just go to the final, yeah.
And the final is cumulative, right?
Final is cumulative in the sense that I might pull some things from the earlier test. I'll tell you like what to focus on, but really the final will be very heavy with the material after exam 3. And really, once we get to that exam, the final, like the stuff after exam 3, you can't really do it without knowing the other stuff. You know, it's kind of built in. There's another problem in the homework. I'm not going to work through the whole thing, but just want to show it to you real quick. This one right here, natural log of the square root. This is the one I thought you were going to ask me about. A squared minus z squared over a squared plus z squared. And then this was, they called this the function capital H of z. Capital H of z equals natural log of the square root of all this junk. And you're asked to find the derivative. So we, again, could do the chain rule. Okay, so let me just show you the chain rule. Don't necessarily write this down, but let's just look at how ugly this would be. This is natural log of all this, right? So the derivative would be 1 over all that crap, right? 1 over all that stuff times what? The derivative of what? The derivative of the square root of all that junk, right? So derivative of natural log of something is 1 over that something. So that's all that stuff in here. If you want, you can put this in parentheses like that. Okay, and then I have to do derivative of the square root of something, which is 1 over 2 times the square root of all that stuff, right? Then times, and now would come your quotient rule, right? Do you see that? Not fun. So instead, what would be easier would be first to rewrite this as that to the 1/2. So the 1/2 power is acting on this, right? Not on the whole thing. It's just acting on this. And then use properties of logs that allows you to take powers and pull them out, right? So I'm just going to pull the power out. I'm not doing a derivative, right? This is not the same as me pulling a power out when I'm taking the derivative. This is just a property of logs. And then what do you think I can do now? Do this division inside of a log, split it into 2 logs. And so that would become half natural log of the a squared minus z squared, then minus natural log of the a squared plus the z squared. Is that correct? No, yeah, that 1/2 has to impact both of these. If this splits into 2, then it has to impact both. So I can put it like this, or I could have just put a 1/2 in front of this. It's really up to you. Now, if I differentiate this, it's a little bit easier because, you know, derivative of that's just 1 over this, and then times derivative of this, and so it'd probably just work out a little easier that way. Just be aware of that on those natural logs. Okay. I'm going to do something a little bit off topic, but related to something we were talking about last class, just because it's been bothering me. Last class, we were talking about decimals and different bases, right? And I was showing you, like, if you take the number like 482, if that's in base 10, I showed you how you could convert that over to like binary, right? Which is like base 2, or you could do like to hexadecimal, right? I showed you that? Yes? Or did I show you the other way around?
You showed us the other. The
What did I
binary
show?
to base 10.
Yeah, I showed you how to go from binary to,
Yeah, you did show us how to go from base 10 to hexadecimal.
I don't think I did. I'm pretty sure, yeah, so let me rewrite this, hold on. Last class, I didn't do that. I gave you something in binary and then we converted it over to base 10. I never gave you something in binary or in hexadecimal. No, wait, hold on. What did I do?
Give us a base 10 and then convert it to binary or hexadecimal.
Someone has it written down, no?
We have the variable.
Forget what I did.
The variables, like,
I'm pretty sure that I gave you like a number like 0, 1, or 100, and I said let's convert that over to base 10.
And I think we went base 10 to the hexadecimal.
Did we? I don't know. I think I gave you hexadecimal.
Yeah, it was in hexadecimal.
Oh, we did.
Yeah, I gave you, what was it? 1FA2,
Yeah.
right? And what did we convert that to? What number? What is it?
we use 16 as
Yeah, base 16, but what did, oh, we didn't? Okay, so I don't want to take too much time on this. Last class I talked about how we convert from a certain base over to base 10, but how do we go from like base 10 to like hexadecimal or base 10 to binary? So I wanted to just show you real quick how to do that. Like, let's say we get the number 482 and this is in base 10, right? And let's say we want to go to hexadecimal, right? So hexadecimal basically contains the digits 1, 0, 1, 2, all the way up through 9. And then after 9, you go A, B, C, D, E, and F. And so, you know, this really represents like 10, 11, 12, 13, 14, 15, right? And so we have 16 digits allowed in hexadecimal. So remember that the way this works is if you had, let's say you had a number written in hexadecimal. This first digit, right, whatever it is, it could be any of these, would be how many 16 to the zeros you have. The next one would be how many 16 to the ones you have. The next one would be how many 16 squareds you have, and then this would be how many 16 cubes, and so on and so forth, right? So there's lots of ways to go from base 10 over to hex, but this is the way I like to do it. First, what I do is I figure out what these numbers are. I might need a calculator for this, but 16 to the 0 is really a 1, right? So this column will represent, or this digit represents how many ones I have. This right here is 16 to the first power, so this is how many 16s I have. And then what's 16 squared? 256, that's how many 256s I have. And then 16 cubed, whatever, it's
49.
yeah, it's a huge number, right? So what I do is I look at this number first and I say, okay, how many how many times does 1 go into this? Well, it goes in there a lot of times, right? So I can fit a lot of these in there. I can fit a couple of these in here, right? And how many of these can I fit in here? How many 256s can I get in there? I think just 1, right? So if I take this and divide it by 256, I get 1 in there, right? I get 1 of those, and let me see, 256, subtract. Okay, come on, Robert. 226, right? I had 226 left over. So what I know is this first digit, right? This first digit has to be a 1, because that'll give me 256, right? Now what I need to do is somehow use the remaining 2 digits to come up with what's left over, which is 226. So now I move to 16, and I say, how many times does 16 go into 226? So you got that? 14 point something, right? So it's going to be like 14. And what is 14 times that? Can you do it? What is it? 224. Okay, got it? And then how many are left over? 2. So I know I need now 14 16s. So I'm going to put here, what? Yeah, not 14. I can't use 14. I have to use the hexadecimal. So this is 9, 10, 11, 12, 13, 14, right? That's 14, so I put an E here. Okay? And then how many do I have left over? 2. So how many 1s will I need to make up 2? I'll need 2 1s. So I put 2 here. So 482 in base 10 converted to hexadecimal is 1E2. All right, just wanted to show that because I felt incomplete not showing you how to go from base 10 to another system. So it's a little more involved with division, but you know. Yeah, once you start getting decimal points, it gets a little more complicated, but it can be done. All right, we are going to continue. We were doing derivatives last time, and I ended class with this weird problem that kind of came out of nowhere where we did this weird log thing. So I'm going to give you the formal notes for this now. We're still in the same section. So this is still 3.3. So we now introduce this thing called logarithmic differentiation. Come on. All right, so we can use the properties of logs to aid us in finding derivatives. This method is called logarithmic differentiation. Here are the steps. All right, so for us, the trouble is going to be when do we use this? And I'll kind of give you some pointers as to when we use this. But here are the steps. Once you've identified this is what you're supposed to do, here's what we'll do. First, we take the natural log on both sides of the equation. After we take the natural log on both sides of the equation, we differentiate implicitly. So that's implicit differentiation. We've done this before. We're going to do that with respect to x on both sides of the equation. And then after we're done, we'll solve for y prime, which to us, this was always dy dx. So if you want to put there dy dx instead, you can. And that's it. Those are the steps. All right, so let me run through a problem, and you'll see hopefully why this is a useful method. So let's start with this. Say we have a function f of x equals, and I'll make it a little bit easier than last class. Let's go x squared square root of x plus 1 over x minus 4 cubed. All right, so right now, if you were asked to find the derivative of this, you could use the quotient rule, right? And when you did the quotient rule, you have to do derivative of the top times the bottom, blah, blah, blah. But when you do derivative of the top, you'd have to do a product rule, and this might get a little messy. It would be really nice, though, if there was a log in front of this. Because if there was a log in front of this, then I could use log of a division, right, to split it up into 2 logs, and then any powers could come out front. All these properties would come into play if there was a log here. So this is where you would have to say, you know what, I'd really like to have a log there. Okay, you have to kind of make that decision. And so what we do, first step, is, well, what did I say the first step was? Because there's actually a step before the first step, I think. I just had it up on the board and I forgot. Yeah, okay, so before I do that, what I'm going to do is I'm going to replace f of x with y, okay? I'm going to replace it with y. I'm just going to call the left side y, all right? That's pretty normal, standard procedure for us. F of x is equal to y. Okay, so now at this point, I'm going to take natural log on both sides of the equation. James and I had this big conversation after class about why this is legitimate, like why you're allowed to take natural log on both sides of an equation. It seems like by doing this, you're perhaps changing things, or just maybe that it's not allowed, right? I mean, that was kind of your concern, right? Is, like, are you really allowed to just take the natural log on both sides of the equation? And technically speaking, we are not taking the natural log of both sides of the equation. We're just using a property of what we call one-to-one functions. All one-to-one functions, you're allowed to do this. I don't want to get too deep into it. I mean, but if you have further questions about why this step is allowed, just talk to me after class or before class. You'll hear me say, I'm taking the log on both sides, but it's kind of not really what's happening. All right, here we go. Let's do the algebraic simplification of the right-hand side. We're just going to leave natural log over there. And as I write, I'm going to write left-hand side, right-hand side. I'm just going to continue writing the equation down. So natural log y equals natural log, okay, top minus natural log bottom. Right? That's a property of logs. No derivatives here. What else can I do? Yeah, so this one will split, right? This one, because we have multiplication here, inside of a log I can split it into two logs also, but this time it'll be a plus between them instead of a minus between them. So now my left-hand side is natural log y. My right-hand side is natural log of x squared plus natural log of the square root of x plus 1, right? But I'm going to write that as x plus 1 to what power? 1/2, because my intention is to pull that 1/2 out on my next step. We can't do any more expanding, like I can't get any more logs out of this, but I have a bunch of powers that I can drop out. So I'm going to drop these powers out. 2 natural log x plus 1/2 natural log x plus 1 minus 3 natural log x minus 4. And now at this line right here, at this line, I am ready for differentiation, because that's about as much as I can do, and I really like what I'm looking at over here, right? These should be easy to take derivatives of because they're separated by addition and subtraction. Numbers out front will just come for the ride. But we have to take derivative on both sides of the equation implicitly with respect to x. So when we take the derivative, I mean, technically you could say we're doing derivative with respect to x of the left, and then the right side we're doing derivative with respect to x of this side also, right? So on the left side, what is the derivative of natural log of anything? 1 over that anything, right, which is y. But then chain rule says now you take derivative of y, which isn't 1, right, because we're differentiating with respect to x. So this is dy dx, or y prime, however you want to write it. Equals, now on the right side, these are all going to be your traditional derivatives because they all have x, right? There's no y's on the right-hand side. So the derivative of 2 natural log x is 2 times 1 over x, right? 2 comes for the ride, derivative of natural log of x is 1 over x. Then that could just become 2 over x. Plus, let's see, 1/2 comes for the ride. Derivative of natural log of x plus 1 is 1 over x plus 1. Times the derivative of what's in here, which is 1, so there's nothing else. And then minus 3 times derivative of natural log of that is 1 over x minus 4 times the derivative of what's in here, which is 1 again. So that's it, right? I could slide the 3 up here. I could just leave that there. Or I could distribute the 2 through the bottom. I could put that 2 up there. Maybe I'll do that in the next step, because there is one more step. I want to know what dy dx is, right? dy dx is y prime, and y prime is f prime of x, right? That's what we're trying to find. So I want this by itself. That means I don't want this here, so I have to multiply both sides by y. However, we know what y is, right? Y, in the very beginning of the problem, we wrote down what y was. Y was x squared, square root of x plus 1 over x minus 4 cubed. Right, that's what y was? So when I multiply both sides by y on the next line, get dy dx equals, I'm going to have all of this, right, times y, which is that. So I'm going to write 2 over x plus 1 over 2x plus 2. So put the 2 on top, distribute the 2 through the bottom, minus put the 3 on top. All of that, right, times that. And that's it. Just leave it like that. Is that your question? Yeah, I mean, because from here, the only thing you could do algebraically is like distribute that here, here, and here. And it would just look ugly, but I mean, you could do that, right? But that's good enough.
Will the homework solutions have us distributed?
I'm not sure. The solution manual, not quite sure what their answers are going to look like. It's not as bad as it looks because, like, look, if I just distribute this here, 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 let's just look at what this first one would be, here to here. That would give me negative, then the 3 would go on top, x squared, square root x plus 1, and then what would the denominator be? X minus 4 to the 4th power, right? Because it would be this times that, and now you have the same factor, so it'd be squared. And then each one of those would have, you know, would similarly go that to something, right? And then maybe you get a common denominator and put them together. All right, that makes sense? All right, so on your homework, I had you stop and not do anything from 51 on, right? You should be able to handle at least 51 and 52, 53, 54. So I'm giving you well, actually the book tells you on numbers 51, 52, 53, and 54, use logarithmic differentiation. So they're giving you that heads up. Take log on both sides and then use properties of logs, then take your derivative. All right, so we get to now something new, still within the same section. We want to take the derivative of some functions, but I'm going to give you some functions here that you probably have never seen before, all right? So let's start out with a very nice one. Here we go. What if I give you f of x equals x to the x, and ask us to find f prime of x? All right, x to the x is a function you have not seen. I'm going to guess that you have not seen that function ever. And what I want you to kind of think about here is this. Let's say I gave you a function like this. I'll call it g. What if I gave you the function x squared versus the function h of x equals 2 to the x? What is the derivative of this one? 2x. What's the derivative of this one? 2 raised to the x times natural log of 2. Right? That's what we learned last class. There's a difference between these two. Here we use the power rule because your variable is in the base and the exponent is fixed. Here, this is exponential, so you have to use the rule for exponential because your variable is in the exponent and your base is fixed. What about this? It's neither one of those, right? Right? It's not this. It's not a power function because for a power function you need this to be a fixed number. And it's not an exponential function because for this to be exponential, this has to be a fixed number, right? This is some weird like hybrid version of both, yes? So how do we take the derivative? Because you can't use either one of those rules. The most common mistakes I see for an answer on this are x times x raised to the x minus 1. What's that? That student did the power rule, right? They brought the x out, they subtracted 1 from the x. That's wrong. Another answer I see is x to the x times natural log of x, which is them trying to use this rule. And that is wrong, all right? These are both incorrect. And that's because to use those rules, this has to qualify as being one of those two functions. So how do we do it? Well, we use logarithmic differentiation, the thing we just talked about. What I'm going to do is I'm going to rewrite this as y equals x to the x. And then I'm going to take the natural log on both sides. And what does that allow me to do on the right-hand side? I can pull that x out front, right? I can drop this x out in front of this. So now my next line is natural log y equals x times natural log x. And now I can take the derivative. But I have to do it implicitly with respect to x on both sides. So when we take the derivative with respect to x on the left, we'll get something. And when we take the derivative with respect to x on the right, we'll get something. And let's see what we get. So left side is going to be 1 over y times dy dx. Isn't that kind of going to happen every time? Every time you do logarithmic differentiation, the derivative of your left side is going to be 1 over y dy dx. It's just always going to be that way. Now the right-hand side, you have to look at what you're doing. So here we have product, right? So you have to use a product rule. So we're going to go derivative of this times this plus derivative of this times this. So derivative of this, 1 times ln x plus derivative of ln x, which is 1 over x times this one, which is x. That's just ln x plus 1, isn't it? Okay. So we have 1 over y times dy dx equals natural log of x plus 1. Last step, multiply both sides by y. And what is y for us in this problem? X to the x. So natural log x plus 1 in parentheses times x to the x. That's it. I just distributed the x to both of those. Wasn't this right here by itself like one answer I gave you that you could do like incorrectly? Right? It's like almost, it's like it wants to be that answer, but you got this other stuff here, you know. Okay, that's it. We're done with that. Make sense? Let's look at that function real quick. Let's look at x to the x. Is this function defined at 0? What do y'all think? When I graph this, is this going to give me a point at 0? Do I have a picture at 0 or no? Can you plug in 0 to the 0? Zero to the 0 is a weird thing, isn't it? Because what's anything raised to the 0 supposed to be? Okay, but what's 0 raised to any power? 0? You can't do it. 0 to the 0 doesn't make sense. It's undefined. But I'm curious to see, how about if we plugged in 1? Can we plug 1 into this function? Can you do 1 to the 1? Sure. Can you do 2 to the 2? 3 to the 3? Can you do 1/2 to the 1/2? Yes? Okay. Can you do negative numbers in here? You're going to run into some problems. Yeah, let's just graph it. Here it comes. Oh, whoa. What the heck is going on there? What happened to all those pretty dots? They went away. Where are they? They were just there. I only see one of them now. Let me bring this back out here. For some reason, it's showing the dots this way, not the other way. So we said at 0, you can't plug 0 in, can you? But it looks like you can. It looks like the answer is 1, right? There's actually a hole there. There's a hole on the graph right there. If you go to the right, you plug in any positive number, this thing is defined. Oh, cool. How did I do that? Oh, that's kind of neat. It's saying it's 1. That ain't right. Okay, so now over here to the left, it's jumping around because there's like imaginary numbers sometimes, and sometimes there's not imaginary numbers. So, all right, I just wanted you to see the graph because you have not ever seen that graph before.
How would you make sense of all those dots? Are you saying that those are maybe ifs?
They're what?
Like they could maybe be there?
They are there. They don't exist for certain numbers. So like here would be example. If I were to ask right now, like, what's f of a half? Let's say that would mean 1/2 to the half, right? Which means square root of a half, and that makes perfect sense. So if I go out to 1/2, square root of a half is going to be up here, right? And for any positive number, I can do this. But what if I do like f negative 1/2? That's going to be negative 1/2 to the negative 1/2, right? Which is 1 over negative 1/2 to the half. So all I did there was negative exponent means take this thing and drop it down. Yes? And then this just means square root. So I'm trying to take the square root of a negative number, which I can't, right? So at negative 1/2, I have nothing. But what about at negative 1? F of negative 1 would be negative 1 to the negative 1, which is 1 over negative 1 to the positive 1, which is 1 over negative 1, which is negative 1. So at negative 1, I have negative 1. It's not showing it, but it's there. Okay? But if I try 1/8, let's say I try negative 1/8, I'm going to have the same problem of an imaginary number because I'm taking an even root of a negative number, right? But that would happen at 1/8, it would happen at 1/2, it would happen at 1/4, it would happen at 3/8, it would happen at 5/8, it would happen any eighth root, right? So there's like any fourth root and any square root. So there's like an infinite number of places in here that I can't do it, right? But there's also an infinite number of places that I can. So you get this thing, we call this like a salt and pepper function. It's just kind of sprinkled everywhere, but it's definitely not continuous. Can't draw it without picking up your pencil, right? And so in a class like this, we are not interested in the graph of this way. We're only interested in it that way. Does that answer any questions? Okay. Yeah, so we don't go that way, right? We just stay away from it. We just make sure, like on a problem like this, we would be, our implied domain here would be x greater than 0. All right. So that's it for this section. We're done. Okay, you have derivatives of exponentials and logs. You have implicit differentiation. I highly recommend, regardless of what your homework says, I highly recommend that you do problems 51 through 60. All right, all of those are implicit differentiation problems, 51 through 60. on section 3.3. All right, we're going to move on to the next section. And the next section that we have is inverse trig functions. All right, and I don't want to get too bogged down in this, but I have to just make sure we're all at least somewhat comfortable. Remember in pre-cal, when you're learning about the sine function, we defined a function f of x to be sine x. We learned what its graph was, right? And we asked ourselves in pre-cal, does this function, well, first, is it a function? Does it pass the vertical line test? Yes. Then we said, okay, does it have an inverse? And we said what? It would have to pass what test for it to have an inverse? Horizontal line test. And the way it's drawn right now, it does not, right? So what we did to get around that is we cut our picture and we restricted the domain so that it still, well, let me show you the restriction. What we did is we said if we restrict the sine function between pi over 2 and negative pi over 2, so we take this function here and we just draw it between negative pi over 2 and pi over 2, then we get that picture. And that picture is a function, pass the vertical line test, and pass the horizontal line test. So it's invertible, has an inverse. And it also achieves its entire range. So the range is from -1 to 1. And on this little snippet of the function, it achieves every value between -1 and 1. So from that, we went and defined the inverse trig function, or the inverse sine function. This all kind of ring a bell? So this is only valid, this inverse sine function, what it does is it spits back the angle. If you plug in a number into this, it'll spit back the angle it came from. So if you say, like, what's sine inverse of 1? It's telling you here, in this picture, where's your y value 1, which would be? Pi over 2. So the answer to this is pi over 2. And then if we did, like, what's arc sine or inverse sine of 0, you'd say, okay, here in this picture, where is your y value 0? At 0, right? Okay. This is just to give you a reminder of the way things worked in pre-cal. Then we did the same thing for cosine, and then we did the same thing for tangent, right? Do y'all remember the domain restriction when we do cosine? It's not that. 0 to pi. And then do you remember the domain restriction for tangent? Same one. With one exception, you have to make it open interval because it doesn't include the endpoints because it's undefined there. Okay, so what we want to talk about today, and this is going to be very fast, okay? We will not go into detail about inverse trig functions. I'm not going to sit here and reteach it. All we want to know in this class is what are their derivatives. Right? It's Calculus 1 class. We know the derivative of a lot of things now, right? We know derivatives of power functions. We can do product rule, quotient rule. We know the derivative of sine. We know the derivative of cosine, tangent, secant, cotangent, e to the x, logs, right? We can take derivatives of all of those. Even weird ones, x to the x, we can do that. What we haven't talked about are what are the derivatives of those 6 inverse trig functions from pre-cal. And here they are, okay? Here they are. I'm going to prove the first one to you. That's it. And then after that, the rest you could prove the same way, all right? So I'm just going to show you why the derivative of arc sine of x is equal to 1 over the square root of x, 1 over the square root of 1 minus x squared. I'll prove that to you, and then these I'll just tell you to, these are on your formula sheet, okay? So you ready for me to prove this? Yeah? Okay, great. You sound excited. All right, so let's call this function y equals arc sine of x. All right, there it is. And I want us to find y prime. Okay, so I want us to take the derivative of that. Let's act like we don't know what it is. All right? So what we're going to do, well, we can't take the derivative of both sides, right? I could take derivative of this. That would give me dy dx, right? But then I need to know what the derivative of arc sine of x is, which is what I'm trying to figure out, right? So what we do is we use the only thing that we do know, and that is the derivative of sine of x. That's cosine x, right? So what I'm going to do is I'm going to take sine of both sides of this equation. And the reason I'm taking sine is because when I put sine together with its inverse, they wipe each other out, right? So long as you're within your domain restrictions, this works. So the right side of the equation becomes x. The left side of the equation becomes sine y, yeah? Okay, now, we want to know what y prime is, right? We want to know dy dx. Does it make sense that right now at this point I could take the derivative on both sides with respect to x? And when I do that here, because of chain rule, I should get the dy dx to pop out. So my derivative with respect to x on the left side, my derivative with respect to x on the right side should yield, what is this? Cosine y times dy dx equals 1. Right? Y'all agree? Okay, so let's solve for dy dx. If I solve for dy dx, I have to divide both sides by cosine y, don't I? So dy dx is equal to 1 over cosine y. And by definition, what is 1 over cosine y? Isn't that secant y? Okay. There we go. The derivative, right, dy dx, which is what I was trying to find, is secant y. And that is what I was trying to show. What? What's wrong? This is what I was trying to show, right? That's what we showed. So this is in terms of y, isn't it? This answers in terms of y. That answers in terms of x. Somehow, I need to get this in terms of x instead of y. Understand? So here's how I'm going to go about doing it. I'm going to use a reference triangle. And those of you going on to take Cal 2, reference triangles come into play quite a bit. What I'm going to do right now is I'm going to go back to the second line that I had that was this equation right there, right? And I'm about to draw a right triangle based on that equation. Here's my right triangle. And I'll do it over here because it's like scratch work I'm going to do here on the side. Using this equation, I'm going to draw this right triangle. Okay. The angle is y, because when you do sine of something, this is an angle. Sine of y must be x, right? Now, on a right triangle, sine of an angle is the opposite over hypotenuse, right? So if I look at this side as a ratio, x over 1, right? Then if I draw an x here and a 1 here, do you all agree that this right triangle is representative of that equation? Yes? This equation and that triangle match up. Now, I'm interested in knowing what secant of y is. And secant of y is, well, what's cosine of y? Off a triangle, cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. And this side is the adjacent side, but I don't have it. But I have the other two sides, right? So if I wanted to know what this was, let's call it a for adjacent. I know a squared plus x squared equals 1 squared, just Pythagorean identity. And solving for a, first we solve for a squared. So move the x squared over and then take the square root on both sides. So that's what a is, right? I'm supposed to do plus or minus, but I'm only doing plus because a is the distance, right? So I'm only looking at the positive answer here. And so now hypotenuse over adjacent is going to be 1 over the square root of 1 minus x squared, which is secant y. Y'all follow that? So dy dx is 1 over square root 1 minus x squared. Now my derivative is in terms of x instead of y. Questions? You do not need to know how to prove these, all right? But again, if you're going into Cal 2, you need to be comfortable with this idea because it's, like I said, it's going to come up quite a bit. At least within one little section of the class, you have to do this a lot. So just out of these trig, inverse trig functions, when you look at these derivatives, there's 6 of them, right? You have the derivative of arc sine of x is this. Derivative of arc cosine of x is this. What's the difference between these two? There's only a slight difference. There's a negative sign, right? On the second one. And then what's the derivative of arctangent of x? 1 over 1 plus x squared. This one right here, I would just burn it in. Burn that one in. That's used a lot in Cal 2. Now the other 3, I wouldn't worry too much about. Just know that they exist and know where they are on your formula sheets, right? All right, so what reference page is that on your formula sheets? Probably reference page 5. 5. What formula? Which formulas are they? Can I see? So 19 through 24. Formulas 19 through 24 on reference page 5 are these formulas. So let's see if we can't take some derivatives then. All right, so here we go. Y is equal to the natural log of arc sine of square root of x. Okay, so we're going right into the frying pan here, all right? We want the derivative of this. See composition? Natural log of arc sine of square root of x, right? So we've got composition, so a lot of chain rule here. So when we start this off, we first have to take the derivative of the natural log part. So derivative of natural log of arc sine of root x is going to be 1 over arc sine of root x, right? That's the derivative of the natural log part. Times. Now we take derivative of arc sine of this, right? This is the first time we take the derivative of arc sine of anything. The formula says what? The derivative of this is equal to 1 over square root of 1 minus x squared, right? Could I have gotten any sloppier with that? Okay, so it's going to be 1 over, right? The square root of 1 minus this thing squared, which is just going to be x, but I'm going to put square root of x squared so everyone understands where that came from. Times, now the derivative of the square root of x, which is 1 over 2 root x. That's the derivative. And then we could just continue. Now everything still works the same way. Like if we had a product, we could do product rule, and right. So if you'd like, you can practice some of these problems. I don't believe this is in the homework. Someone check for me on the homework list. Is 3.5 homework in there? Is there 3.5 homework? Here, I have it right here. I believe you. 1 to 6, and then 16 through 27. You can skip 1 to 6 if you know how to do them. All right, like if you're comfortable with them, because that's going to take you back to pre-cal. You can, if you just want to work on derivatives, it's 16 through 26, or what did I say? 27, yeah. Okay? And I'm not going to give you anything more because it's really at this point, you know, we could practice, but I'm hoping at this point you understand now. You just have a new formula, you just have to apply it. Yes?
So I just want to clarify, if it was y equals natural log of inverse or arc sine of square root of x plus 2, then in the second step it would be 1 minus x plus 2 squared, right?
You're saying if this was square root, wait, which part?
So it's x plus 2 instead of square root.
You don't want the square root?
Well, like, I'm just saying hypothetically to understand.
Yeah, but if you're saying take this out, or leave the square root in,
Take the square root.
and make that an x plus 2?
Yes.
Yes? Then this would be x plus 2, 1 over, right, the square root of x plus 2 squared, and then this wouldn't be here, because the derivative of x plus 2 would be 1.
Okay. Thank you.
Mm-hmm. All right, so we've reached a critical point in the class. We have now discussed all the types of functions we will be taking derivatives of. All right? There's no other groups of functions that we need to learn the derivatives of for this class. In Cal 2, usually you start out and we go, oh yeah, there's these functions called hyperbolic trig functions. And when you learn about those, and then you learn about their derivatives. And then you learn about the fact that they have inverses. So then you learn about the inverse hyperbolic trig functions, and then you find out what their derivatives look like. So there's another 12 functions that you have to learn, but just not here, all right? So we're done. So we're going to do one last thing in chapter 3, and then we're finally going to move on to how do we apply all of these derivatives to something, right? Like, what are we going to do with this now? Now that we know how to differentiate things, what can we do with it? But we have to finish chapter 3, and it finishes in the almighty chapter 3, section 7. This is one of the best sections in the book. So see hyperbolic functions here? I'm not covering these. That'll be in Cal 2. So we are going to talk about indeterminate forms and L'Hopital's rule. So this right here looks like it's spelled hospitals, but it's L'Hopital. L'Hopital. All right? So we're going to talk about L'Hopital's rule, but we first need to talk about this thing called indeterminate forms. So we're going to go back right now and talk about limits. Your favorite topic, limits. That's your favorite topic? Yes. So remember when we were doing limits, there was like one of the first limits I ever gave you that was kind of weird was this one. Remember that one? Do I remember what that is? That's equal to 1. And do you remember why it's 1? Sine junk over junk, right? But did I show you why it's 1? I never did. I just told you it's 1, and I told you don't ask questions, all right? Right? Just accept it on faith. And if you wanted to know how you could show that that's 1, you could come by my office. I could show you a really fancy geometric proof, right, as to why this is 1. But the issue we had was when we tried the limit, we got 0 over 0, right? And remember that sheet I gave you with all the little forms? Anytime when we take a limit and we got 0 over 0, we always tried to do some algebra or some trick, right? And here with sine x over x, there's no algebra you can do. There's no trick you can do. You can't factor, you can't cancel, you can't come in with the conjugate. There's nothing you can do algebraically to make that turn out to anything that's going to get you to 1. So we have 0 over 0. We have a problem, right? All right. We also had problems in class where we got